Okay, welcome to Biology 1412 and 1400. Today we're going to be talking about water. Okay, so today basically I want us to talk about the dipole nature of water. So we'll be looking at why exactly water has a bent shape. So the dipole nature of water and hydrogen bonds. So hydrogen bonds and role of water. So the role of water in general with reference to the nature of water. Okay, so having said that, we're also going to talk about the roles of water related to high latent heat. So the latent heat and specific heat capacity. So specific heat capacity. So this is exactly what we're going to be talking about. So you're going to appreciate why exactly water behaves the way it does. Okay, so having said that, let's get right down into it. So the first thing that we're going to talk about is the dipole nature. The dipole nature of water. Okay, so when you look at the word dipole, one thing that we must realize is that when a molecule is dipole, it means it has two charges, okay, partially positive and partially negative. So when we talk about the dipolar nature of water, we are referring to, we're going to be talking about polarity very much in this section. So when you look at polarity, it is basically the unequal distribution. So it is an equal distribution. Okay, so the reason why I'm actually highlighting this is because at your own time you are able to go through and actually understand what exactly we are talking about. So when you look at water, you will notice that we have the chemical formula of water, which is H2O. And when you look at H2O, we have the oxygen atom being the central atom because it's more electronegative, okay? Meaning it attracts electrons more to itself. And we have it is bonded to two hydrogen atoms. So why exactly do they say it's unequally distributed? Okay, so let me take you back to covalent bonding. Okay, so when you look at this oxygen atom, it has 6 electrons in its outermost shell, and oxygen is found in period 2. Yes, so it has 2 shells. So we have 1, 2 shells. And when we're arranging this number of electrons into the shells, you notice that the first shell is going to have 2 electrons. So we have 2 electrons there, and the last shell will have 4 electrons. So 1, 2, and 3, and 4. So what you notice is that the electrons that are inside and that are close to the nucleus are very tightly bound to this nucleus, right? Because in this nucleus we have what we call protons and neutrons, and the electrons that are surrounding this nucleus, they are actually negatively charged. Protons are positively charged, and neutrons are, they have no charge. So when you look at this, you discover that the outermost shells have the electrons that are able to participate in a chemical reaction. Okay, so when you look at hydrogen, hydrogen will covalently bond with water in such a manner such that it's going to donate an electron. So there's an electron coming from hydrogen, so that these two are going to be stable. So this is hydrogen right here. Now I want you to notice something. Okay, according to atomic structure, we're going to note that protons, the number of protons is equal to the number of electrons. Okay, so here's the reason why this important is very, this point right here is very important. So when you look at the number of protons is 6. So there's 6 protons in the nucleus. Okay, this is to say that there are also 6 electrons. So we have 6 protons and 6 electrons. So now that we have 6 protons in the nucleus, okay, it means these protons that are positively charged have a higher affinity. And what I mean by affinity, I mean they have a higher attraction for electrons that are coming from hydrogen. So the protons are pulling the electrons from the hydrogen atom. This is why we say the oxygen atom is more electronegative, okay? So it's pulling electrons towards itself, okay? Because positive and negative, they attract each other, unlike pose, okay? So these protons are actually attracting the electrons from the hydrogen. Hence, because they are attracting electrons to the hydrogen, to the oxygen, this means that they will leave hydrogen with a net partially positive charge, okay? Because for hydrogen, we know that it has 1 electron and 1 proton, okay? So it means if this 1 electron is being put towards this oxygen, 1 proton is going to remain, and this is going to make it have a net slightly positive charge. And because this oxygen is receiving, or rather it's attracting more electrons to itself, it will have a slight negative charge, like you can see. Okay, so when they say polarity is an equal distribution, it means these electrons are not shared equally. Because if they were shared equally, it would mean, let me give an example. What they mean when they say equal sharing and unequal. So like you can see, this is the reason why water has a dipole nature. And then when they talk about an equal distribution, they're just talking about, for instance, we have, let me give an example of hydrogen. Hydrogen has 1 electron and 1 proton. So when it's sharing, it has 1 there and 1 there. Let me just use a different color. So this is hydrogen 1 and this is hydrogen 2. Okay, so when these two atoms are sharing electrons, they share them equally. This is to say that you will not find any other electrons in the outermost shell. There will only be these 2 electrons that are sharing right here. Okay, meaning the electrons are being shared unequally. But when they've been shared equally, but when you look at water, the electrons are unequal, such that oxygen even has spare 2 electrons, like you can see, since there were 4. So electrons are negatively charged, as you can see. So that's what gives oxygen a slight negative charge due to its electronegativity. Okay, so this is what we mean when we say water has a dipole nature of water. So when we talk about dipolar, it means I've explained about polarity. Okay, so polarity is an equal distribution, which will make, so when you talk about polarity, just think of charges. Okay, so you think of charges. So when it's di, it means it has 2 charges in its atom, or rather in its molecule. So when you look at this molecule, water has a positive charge, a slight positive charge, and a slight negative charge, like you can see. Okay, so that's what we mean when we say the dipolar nature of water. Okay, and then another important concept we're going to realize is that the electrons that are involved. Okay, let me just draw another water molecule. So we have hydrogen here. So these electrons, we call them lone pairs. Okay, this is a lone pair, meaning it did not participate in bonding. This bonding that you're able to see right here, this single bond. These are lone pairs. So what you notice is that basically water is supposed to be linear in shape. Okay, we have water here. Okay, so the natural shape of water was supposed to be linear. When I say linear, I mean a straight line. So what happens is that these electrons that you can see right here, we know that they are negatively charged, right? what happens is that these electrons repel these electrons that are involved in a bond. So because there is repulsion, it causes this bond to be pushed down there because they don't want to be close to each other. Okay, so this is what causes water to actually have a bent shape, because these electrons don't want to be close to each other, so they push each other away. So the lone pairs will push these electrons downward, making water to have this shape that we can see. So water has what we call a bent shape. It looks like it's bent. Okay, that's why water has this shape. And then because of this arrangement, you notice that there's an angle that is formed. Okay, there's an angle that exists between one hydrogen atom and the next hydrogen atom. This is to tell you that water has 104.5 degrees. Okay, so this is the approximate angle that is formed due to the arrangement of the electrons and how they actually push the other electrons downward. So this is why water has this bent shape. Okay, next thing that we're going to talk about is, we are still talking about water and its factors. So the next thing that we highlighted was the hydrogen bonding. Okay, so I need you to notice that whatever point we talk about right here is connected to a different point in the next. Okay, so we're going to link the dipolar nature of water to hydrogen bonding. Okay, so the next thing we're talking about is hydrogen bonding. Okay, so what exactly is hydrogen bonding? Okay, so when you talk about hydrogen bonding, we talk about the attraction between the hydrogen. So there's an attraction that will occur between this hydrogen atom and an oxygen atom of a different water molecule. So this is what we mean. So we have water here, right? And we know that it has a dipole nature. Okay, and a negative. So what happens is that this water is going to be attracted to a different water molecule. Of course, we know that opposite charges attract. So what you notice that if this oxygen is slightly negative, it means it's going to attract a slight positive charge on a different water molecule. Okay, so this is what will happen. This oxygen will be attracted to a positively charged hydrogen atom on a different water molecule. Okay, and the hydrogen atom will be attracted to an oxygen atom because they have opposite charges. Okay, so there'll be a slight attraction. Now this attraction is what we are calling hydrogen bonding. Okay, so like you can tell from the name, hydrogen bonding has to do with the name itself. Hydrogen bonding means hydrogen is involved. Now when you look at this hydrogen bond, you notice something that I actually used faint lines. Okay, these lines that you're able to see, I didn't use a solid line because the bond is actually weak. So the bond is weak. Okay, so the hydrogen bond is weak in nature. Okay, and it's being formed due to the attraction between the oxygen and the hydrogen of different water molecules. Okay, because they are charged. Okay, so what you notice that this hydrogen bond, when it's just an individual, when it's an individual bond, what I mean is that when it's just a single hydrogen bond, it's very weak. But when you find multiple hydrogen bonds, it's strong. So when we have multiple hydrogen bonds, they're going to be strong. Okay, so this is why you find molecules like DNA, where it's supercoiled and the like, they have hydrogen bonds in between, but it is very stable. So we have hydrogen bonds here. So you may be wondering, how come the bonds that are in DNA are very weak, at the same time they're very strong? It's because on its own it's very weak, but when there are many of them, they're relatively very strong. Okay, so this is what we mean by hydrogen bonding. Okay, having said that, we'll move to the next segment where we'll talk about why exactly water is a solvent. Okay, why is water a solvent? Okay, so we're talking about water as a solvent. Okay, when you look at a solvent, you notice that if something is able to dissolve in water, we're calling water a solvent because it enables other solutes to dissolve in itself. Okay, so when you look at that, what you're going to notice is that because water has this dipolar nature, okay, it has different charges, which is slight negative and slight positive. Okay, so because of this, you find that molecules that have two charges, for instance, the sodium chloride, okay, this sodium chloride is formed due to ionic bonding, like we know. So when you look at the sodium chloride, okay, you notice that sodium has a positive charge and chlorine is negatively charged, like you can see on the periodic table. Okay, this is a halide, this is a metal. So the two atoms are attracted to each other quite strongly. So what you're going to notice is that this sodium atom that is positively charged, when we put it in water, okay, so if this is a glass of water, and by the way, sodium chloride is table salt. So when you put salt in water, you notice that it quickly disappears. Why exactly does it disappear? It's because when you put sodium chloride in water, it would dissociate. So what we mean by dissociation, okay, when you look at this word, it means it will split into its individual atoms. So if it's sodium chloride like this, it's going to be sodium plus and chlorine plus, meaning this has dissociated. So what do they mean by saying it? Because it's dissociated, it will be like this. It will mean the positive part of water is going to be attracted to the negative part of this salt that we have dissolved. Okay, so this is to tell you that chlorine is going to be attracted to the hydrogen atom on water, right? So this is the oxygen. So chlorine atoms will be attracted to the positive end of water, whilst the sodium chloride will be attracted to the negative part of water. Okay, so you find there's the oxygen side will be facing the positive atom because of the different charges that we have, and the same thing will happen. Chlorine will be facing hydrogen because of the opposite charge. So because of this, we have what we call a lattice. So you can imagine it like it's a box of many sodium and chlorine atoms. Okay, if this is a lattice, you find that here there is sodium chloride, so many atoms of sodium chloride are in one salt. So what you notice is that water molecules are going to surround this lattice, okay, according to what they are being attracted to, according to what side. Okay, so because of this, they'll break it down in such a way that it's going to crumble. So this part is going to be attracted to water and the other part is going to be attracted to water, until finally the pieces are actually separated. So they make this lattice to actually decrease. So what happens is that the reason why you see that this salt appears to disappear, it's because the atoms are no longer close together. The distance between this sodium and this chloride, the distance between these two atoms is relatively very large. Hence you can't even see this, because now they're existing as their individual atoms. So we have one sodium atom here, and the chloride very far from it. So this distance that you're able to see because of separation is what is going to cause disappearance. Okay, hence you find that this molecule actually dissolved in water, and you're unable to see it. Okay, so some of you may be asking, how come the more we put salt, it ceases to disappear? Okay, the reason why, it's because all the water molecules would have been involved in trying to dissolve this. Hence, the more you put salt, you will not have any other water molecules to interact with that salt, because they're all busy trying to dissolve the other salt molecules. Hence, this is why we have a saturated solution, because those solutes have no water molecules to interact with. Okay, so this is why water is a very good solvent. Okay, and having said that, I want to highlight something. So for something to dissolve in water, it must also have two charges. It must also be polar. Okay, so for something to dissolve in water, it must be polar. So this is to tell you that if something is non-polar, it will not dissolve in water because it cannot interact. So for non-polar, there is no interaction. Okay, there is no interaction between water molecules. So this is what we mean when we say water is a very good solvent. Okay, another thing I would like to highlight is the same thing about non-polar substances. We're going to talk about what we call phospholipids. Okay, so we have what we call phospholipids. These phospholipids have a hydrophilic head. So when we say it's hydrophilic, it means it loves water, right? It loves water. And then the tails, okay, this tail is a hydrocarbon chain, meaning it has many carbon to hydrogen bonds. Okay, and this tail is actually, it's water hating. It hates water. Okay, so when you look at this, when we put this non-polar molecule in water, it will not dissolve. So this is why you find, for instance, oil will just be floating on the surface of water because it can't dissolve inside. Okay, because it is non-polar. So what you notice is that the head, which is water loving, will interact with water. So if we have water molecules in this environment, this hydrophilic head is going to interact with the head. It's going to interact with water. Okay, then the tail is going to shun away from water, to face away. So we'll have many tails looking like this. They'll be facing away from water, and others also on the other end. Okay, this is why we have a lipid bilayer commonly found in cell membranes. Okay, which will be learned further on. Okay, so this is what causes water to arrange itself in such a manner. Okay, having said that, we're now going in our next segment, where we're talking about the role of water in relation to a high specific heat capacity. Okay, so let me just use a different marker. So role of water, so we'll talk about high specific heat capacity. Okay, so when you talk about high specific heat capacity, we first want to know what exactly is specific heat capacity. So specific heat capacity is the amount of heat. So it is the amount of heat that is required. So that is required to raise the temperature of water, of 1 kg water, so 1 kg of water to, or rather by 1 degrees to 1 degrees. So when you know this definition, automatically you're going to connect with why water has a high specific heat capacity. So if we say the specific heat capacity of water is 1 kilogram per calorie, okay, let's just assume these are the units. It means you need, actually let me just I think I've swapped. It's supposed to be 1 calorie per kg. Okay, let's take for instance it's 1 calorie per kilogram. It means you need 1 calorie of energy in order to raise the temperature of water at least by 1 degree Celsius. Okay, so this explains why even when you put water on a brazier or any source of heat, it takes long just for it to catch heat. Okay, so why exactly does that happen? Okay, why this happens is because much of the energy is used in breaking the hydrogen bonds. So like we've talked about hydrogen bonds, right? We have this bond connected to water. Okay, these hydrogen bonds that are existing right here. Okay, so we have this as the hydrogen bond. So when you put water on a source of heat, if this is heat that is going on water, instead of this heat, so this is a heat source, instead of this heat trying to separate these two water molecules so that we can increase their kinetic energy and thereby increasing the temperature by 1 degree, what happens is that this heat it tries to break this bond. Okay, now we know that when this bond is multiple, like when we have so many water molecules, so you have so many water molecules in water itself, we don't just have one water molecule. So what you notice is that there are so many bonds, okay, that are in water, such that for us to break these hydrogen bonds, it takes a lot of heat. Thereby, the high specific heat capacity is going to be very high because you need more energy just to raise the temperature of water by 1 degree. Okay, because all the energy is going into breaking these hydrogen bonds. Okay, so this means that the temperature fluctuations in water are minimized. So when you talk about fluctuations, it means water cannot easily absorb heat, right? And water cannot easily lose heat because of these hydrogen bonds. Okay, so water therefore provides a very constant external environment for many cells and organisms. So because of this nature, it means your cells are able to survive because the temperature does not easily fluctuate, or rather it doesn't easily change. Okay, because water has a high specific heat capacity. Because if that was the case, it would mean on a very hot day, it's possible for all the water in your body to evaporate if it was going to easily increase its temperature, but that doesn't happen because of this property of water. Okay, so that's high specific heat capacity. Okay, the next thing we're going to talk about is the density of water. Okay, so the density of water. So when you look at density, we've been talking about density, which is the mass of a substance that is found in a specific volume. Okay, so when you look at water, water is a very strange and at the same time unique element, because when you look at the density of water as a liquid, okay, so when water is a liquid, it is actually dense, meaning it's heavy in a way. Let me use simple terms, meaning there is more mass that is occupied in that volume. But when water is a solid, okay, we expect it to be more dense, but it's actually lighter. So it's lighter, which is quite shocking because it's supposed to be relatively heavy. So we'll explain why exactly is water lighter when it's a solid, okay, instead of it being heavier. So when you look at the density of water, the density of water decreases at a temperature below 4 degrees. So at 4 degrees Celsius, the density of water decreases. So at 4 degrees, density decreases. So this is to tell you, when it was at its liquid state, it was relatively heavier, but as it is becoming more cold, as it is losing heat, it's becoming less dense. Why is that happening? So what you notice is that because water, we have water molecules right here, right? And we know that the hydrogen bonds that are existing because of opposite charges, okay? When water is decreasing, there's a way in which I'm sure you remember this. You know that water has layers that are able to slide on top of each other. So if you have this water, another water molecule can slide over it. So meaning these hydrogen bonds are constantly broken and reformed at the same time, okay, as the water is moving. So what happens that when water is moving, the distance of the hydrogen bonds increases, okay? So when water is losing heat, so we have heat that is being lost. So heat loss, when heat loss is occurring at the time where these water molecules are far apart, it will mean there'll be some sort of a vacuum. So it's like there's a vacuum that's existing right here. There's a space that we're able to notice. And because of that, you find that when water is in its solid state, it's going to be lighter because the water molecules are very far apart. So you find one water molecule is here, another one is there, okay? The distances are far apart, okay? This is why you find that all these are spaces that you can see. All these are spaces. So because of these spaces, you find that water is in its solid state is going to be relatively lighter, okay, as compared to its liquid state, okay? So this is where it has a very low density at 4 degrees, okay? So an application is that, just a minute, let me just erase the board. Okay, one application of this nature of water is certain animals are able to survive. For instance, if this is ice, right, we have ice over there. So if this is the ground floor of an ocean, right, we have fish that are able to survive, okay? Ever wondered why these fish are still able to survive despite the harsh conditions? So this is the environment, okay? So this is the environment and it's very cold. This is to say, in winter season, you find that there is ice, but fish are still able to survive. The reason why is because since ice is lighter than water, it is going to float on water. So ice is less dense, okay? So it's less dense. And remember, the reason why it's less dense is due to hydrogen bonding and not the fact that there is more mass. There is less mass, okay? So it's the same thing if you have a balloon. A balloon has more air in it. That's why it's able to float, okay? So the air in it makes it more lighter. So what happens is that when heat in the water is trying to escape this water, okay, so we have heat loss. What happens is that when it reaches the surface of water, or rather the surface of this ice, the ice acts like a mirror. So this mirror is going to reflect the heat back or radiate it back, okay? So it means instead of the heat escaping into the environment, it is radiated back into this atmosphere, and fish are able to survive because the temperature is going to be kept constant, okay? So that's why we are able to look at water as it having a very small density, okay? So that's about density. Another thing we're going to talk about is the bonds. Approximately how many bonds? So for instance, we have what we call, when we talk about each water molecule actually forms an average of 3.4 bonds with other water molecules. So when you have this water molecule, it forms about 3.4. So what I mean is that this water molecule is going to interact with another water molecule. It will interact with about 4 water molecules. Okay, so what I mean by 4 water molecules is that we can have 1 water molecule there, right? Okay, so this water is attracted to this water, another water molecule is attracted to this one, another one here, and another one, hydrogen, is facing this side. Okay, so approximately we have 1, 2, 3, and 4. So we say water can form about 3.4 bonds with other water molecules. This is what we mean. So this was just an approximation, okay? So this is what explains. So meaning when the distance here increases, we'll have 1 water molecule here, another one here, another water molecule here. Hence, due to this distance that you can see, okay, there's space here. That's what water makes it. That's what makes water light in its solid state. Okay, so I just felt the need to actually highlight this point. Okay, so the other thing we'll talk about, the 2 last things that are actually going to be talked about are the cohesion and adhesion forces of water. Okay, so this will take very few minutes. Okay, so as we are talking about the properties of water, we're going to talk about the role of water related to water's cohesion. So cohesion and surface tension. Okay, so we have what we call cohesion and surface tension. So what happens is that when we keep on talking about hydrogen bonding. So when we have water molecules that are here, right? We have what we call cohesiveness. So cohesion is basically an attraction between like molecules. So attraction between like molecules. Okay, so because these molecules are alike, they're going to attract each other due to them having opposite charges. Okay, so this is the same thing that we're able to see, that this water molecule is attracted to this water molecule, so as this one. So meaning that force of attraction is what we're calling cohesion, right? So because water is cohesive, meaning it's attracted to other water molecules, what we notice is that we are going to have surface tension. Okay, so because there is water molecules being attracted to each other through hydrogen bonds, water is going to form some form of a skin, like a very thin skin on the layer of water. So it will look like there is a surface. Water is creating a surface tension. Okay, these water molecules are strongly attracted to each other such that they seem like there is a layer, or rather there is a skin of water. It's just like when we talk about a tap, right? When water is dripping, when you close the tap, notice that the drop of this drop of water that you're able to see, it doesn't easily fall off if you don't open water at this end. Okay, of course it may be due to suction because there's air that is keeping this water from falling, but the main thing that we're going to talk about is the attraction. Okay, all these water molecules, okay, let me magnify the water droplet. So there is water molecules that are being attracted to each other. This one is attracted to this one, so there's a high surface tension that is here. Okay, water molecules are attracted to each other so much that they cause it to have some form of a layer. So you find that this water cannot easily like separate from itself. One water molecule will not easily let go of the other water molecule because it's a long chain of water molecules that are being held. So this is why you find that there are certain insects that are able to walk on water. So these insects, or even a leaf, it's able to float on water. It's like there's a surface. So this insect can easily step there and there because there is a strong surface tension. So if this is water, the insect is able to step right there, okay, on different water molecules, because it's like there's a surface that has been formed due to the attraction of water molecules due to hydrogen bonding. Okay, so that's what we mean by surface tension. The next thing I'll talk about is cohesion, or adhesion, sorry. So when we talk about adhesion, it's a little bit connected to cohesion, but in a different way. So we have adhesion. So when we talk about adhesion, this is simply attraction between different molecules. Okay, so the best way I can explain this is using an example. When you look at water, right, in a container, so if we have this container, you notice that you may try to pour out some water, right? So there is water that is being poured out, but when you're done pouring the water, you still find that there's some water droplets that will remain stuck to the wall, and those cannot easily be disposed. The reason why is that the water molecules are attracted to the surface, okay? They're attracted to the surface of water, okay? So this is to tell you that these water molecules will be strongly attracted to the walls of water in such a manner that they will not easily leave, okay? So there's an attraction between water and the surface. That's why it's adhesion forces. This is the reason why even your clothes are able to get wet. It's because the water is strongly attracted to your clothes. So the clothes are a surface, and then that bond between the water and the surface is what we're calling adhesion forces. Okay? So having talked about adhesion, and remember, one key thing about all this is due to hydrogen bonding, okay? We're going to talk about water's capillarity. Okay, capillarity. So this is, so capillary action, I can even call it capillary action of water. Okay, so what exactly do they mean when they say water has a capillary action? So when you look at, let me just give a basic example. A thermometer, right? It has a bulb at the end. The mercury is able to go to the top. It goes against gravity. Okay, we know that gravity is a force that pulls things downwards, but water is able to overcome this force and pull things upwards. Okay, so why exactly does that happen? It's because when you look at a vessel like this, you notice that because water molecules are attracted to each other. So these water molecules are attracted to each other, and because they're attracted to the surface of this container that we're able to see, they're attracted to this surface, and because they're attracted to each other, they'll move upward in one unit. So it's like when one water molecule is going up, it will pull another water molecule, and that water molecule will pull another water molecule connected to it. So it will be a long chain, okay? And because these water molecules are attracted to the surface, they'll move in one accord. So they'll move together. Hence, this water will start moving upward. So this is what we notice when we're talking about the xylem, the phloem. So the xylem is a vessel in plants that is able to conduct the movement of water from the roots all the way up to the leaves and the stems and so on and so forth. So while we have a plant like this where it has roots, you may be wondering how come water is able to move from, if this is the water table, right? Water is able to be absorbed right there, and then it's able to move and spread out to branches. The reason why is that there's what we call capillary action. So having said that, when we talk about capillarity, we mean there are two forces that are involved, which is adhesion, so adhesion, and cohesion. So cohesion is coming because water molecules are attracted to each other. Adhesion is coming because water molecules are attracted to the surface itself. Okay? So this is what we mean. Alright. So that's the end of our topic on water. That is all that you need to know. So remember, when you want to answer questions on water, just relate whatever you've been learning right here with the questions, and it will all make sense actually. Okay, so we've come to the end of our video.